Hello, my name is Ivan Božić and I'm a PhD student in the Translational Biomechanics Lab at Tulane University. Today I will show you our work on optical sectioning, super-resolution, structured illumination microscopy. In the US, appearance of positive surgical margin after surgical resection of cancer varies with the type of cancer from 4.32 to 35%. The existence of positive surgical margin will influence patient treatment outcome by adding additional oncology treatments or by scheduling another surgery. Furthermore, these additional treatments will increase total healthcare cost. If you are interested in visual pathology of breast and prostate biopsies, please see the following presentations. Increased cost for prostate oncology treatment yearly goes up to 50 million. The main reason for an increase in cost and future treatments is that formalin-fixed paraffin-embedded histology requires from several hours to a few days for tissue processing and making the diagnosis. The main bottleneck in procedure is the tissue fixation and hardening and physical sectioning. Those two steps are not required in virtual pathology techniques that make them a potential candidate for a rapid intraoperative pathology diagnosis. Majority virtual pathology techniques use fluorescent microscopy to produce HNT-like images. In our group, we are working with structural illumination microscopy and light sheet microscopy. But virtual pathology is also possible with confocal microscopy, nonlinear and multiphoton microscopy, and microscopy with ultraviolet surface excitation. However, majority of these techniques are made to mimic current histology procedure by imaging small tissue samples. For virtual pathology, to be able to make intraoperative diagnosis of surgical margins, it needs to be capable to image whole or part of organs with needed diagnostic decision resolution in a short time interval. This brings us to a situation where the space bandwidth product of the imaging system is limiting. Using structured illumination microscopy, we showed that it's possible to image a whole prostate circumference in less than 1 hour. However, this speed is still above the threshold of intraoperative pathology diagnosis. Furthermore, this speed is achieved with acridine orange stain, which labels both cytoplasmatic ECM and nuclei and is not useful for mimicking H&E. On the other hand, we showed that we can image a whole organ with resolution that was acceptable for pathology diagnosis. We believe that structured illumination microscopy is the best candidate for breaking the space bandwidth product challenge in rapid intraoperative pathology imaging because it's capable to perform both optical sectioning and super-resolution, acquiring a larger field of view with the resolution needed for diagnosis in less time. As our current SIM system is based on optical sectioning, we think that incorporating super-resolution not for imaging smaller details, but for resolution recovery that occurs with lower magnification, lower NA objective can help us with space bandwidth product limitations. Optical sectioning for the SIM works similarly as mechanical slicing. The main difference is that we can control the depth of imaging by modulating the frequency of the structured illumination that we use to illuminate the sample. The part of the image arising from the focus will be the only tissue depth in which the projected pattern will sufficiently modulate the image. For optical sectioning, the SIM patterns are simply phase shift prior to reconstruction, where typically only 3 images are required. Where, for super resolution, we need to rotate patterns to better cover the Fourier space, requiring more images to be collected, typically 9 or more. Both optical sectioning and super-resolution SIM are based on convolution of very well-defined illumination patterns and unknown fluorescence dye density. However, for super-resolution, our goal is for the pattern frequency to be as close as possible to the objective cutoff frequency, diffraction limit. This setup will allow us to image high-frequency content outside of the diffraction limit, inside the diffraction limit support region of the microscope. With the proper reconstruction, which is possible because we know the frequency content of the illumination pattern, we will be able to reconstruct high frequency content in the right location outside the diffraction limit. By taking images several patterns rotation, we will be able to create an almost isotropic increase in resolution. Theoretically, resolution can be increased infinitely, but practically, with the first order interference pattern and 3 rotation, it's possible to increase resolution twofold. We can see imaging limitation as a pick-2 choice triangle, where we can choose between the field of view, resolution, and speed. Almost all imaging devices make a compromise between those choices. For example, large FOV will allow us to image fast, but the resolution will be limited. On the other side, if we have high speed and high resolution, the FOV will be limited. Finally, we can have good FOV and resolution, but the speed of imaging will be low due to multiple images taken on the same location as in OCT. Our current SIM system compromises all 3 features to produce acceptable resolution and speed. However, it's currently not fast enough to provide whole organ imaging comfortably within intraoperative time frames. To address this issue, we want to create a system with a good resolution and good speed. Here we define good resolution as a resolution that will allow a pathologist to make a proper diagnosis, and a good speed is a speed that will allow pathological diagnosis during surgery. The most logical approach to increase speed is by increasing field of view. This will increase each framed area such that fewer frames are needed to record the whole sample and will ultimately result in a speed increase. However, as in photography, higher field of view will result in worse resolution. To retrieve good resolution while keeping this large field of view, we will apply a super resolution approach on low magnification, low NA objective. This approach will not show us smaller details in a sample, but rather will allow us to recover information that is lost by moving to a lower magnification, lower NA objective lens. Ideally, we will obtain the same resolution as our current system using a higher NA objective lens, while improving FOV by several fold. The objective of this study was to determine whether SIM could be used for both optical sectioning and resolution enhancement in turbid samples using very low NA objective lens with wide field of view, which is different from standard approaches which use SIM with very high NA objectives with the goal to beat the ultimate diffraction limit. We are using a multi-line LDI6 laser from 89 North for sample illumination, which is coupled into the system using multimode fiber. Light is first collimated and then passed through polarization beam splitter that should pass only as polarized light on the spatial light modulator. A liquid crystal on silicon spatial light modulator creates a vertical sinusoidal pattern with a spatial frequency of 16.3 micrometers. And light is transferred to a clean-up polarizer, which is to remove any P polarization that was not cleaned using the PBS. We use 2 lenses, f1 and f2, to focus pattern interference on the mask and pattern on the tube lens. As we can see, our spatial filter is created with holes to pass only the first order of diffraction of the pattern. Before filter, we have all orders, and after filter, only first orders. It's important to notice a huge reduction in light intensity due to filtration of 0 order. Light is transmitted to dichroic mirror that reflects illumination light toward the sample and transfers fluorescent signal from the sample on the camera. First, we will quantify resolution improvement of optical sectioning super-resolution structured illumination microscopy. For this purpose, we image Ready Optics 2015A USF target that can quantify resolution up to 137 nanometers. We placed a thin layer of agridine orange on the top of the resolution target and used system setup from the previous slide with 470 nanometers excitation. If we magnify smaller groups, we can observe that all elements in group 8 are visibly distinguishable, and that groups 10 and 11 are not resolvable. For group 9, element 1, we can see that all 3 peaks are resolvable after applying Rayleigh criterion in lateral and in an axial direction. A similar procedure we applied for optical sectioning SIM and found that group 8, element 2, is the smallest element resolved by Rayleigh criterion, which represents a spatial resolution of 1.74 microns, and for group 9, element 1, we resolve 977 nanometers in spatial resolution. This gives us a 1.79 factor of improvement in the spatial resolution, which is slightly lower than the theoretical limit of 2-fold for optical sectioning super resolution structural illumination microscopy system in this setup. After resolution quantification, we imaged a turbid phantom with fluorescent beads of approximately 1 micrometer in diameter. Turbid phantoms represents a good model for thick tissue samples. For better analysis and comparison, we concentrated on a small area indicated by a yellow square. If we zoom that area in wide field optical sectioning SIM and optical sectioning super resolution SIM, we can see that first 2 modalities cannot resolve separate widths. To quantify this conclusion, we further select a smaller area of approximately 3.7 times 4.8 micrometers. By plotting the intensity profile, we can see that the bright field image has almost uniform value except on the end of the line segment. In optical sectioning SIM, we see fluctuation centered around average value that look like noise. And for optical sectioning super resolution SIM, we see a clear change in intensity distribution that varies between high and low intensities for more than 200 points. We use this intensity profile and fit it with the Gaussian distribution that showed us 3 clear peaks that represent 3 beads, with full width half maximum of each peak, which is near to bead diameter. In conclusion, we demonstrated optical sectioning super resolution structured illumination microscopy with low magnification low NA objective. We achieved 1.79-fold improve in resolution by adding super resolution capability onto optical sectioning SIM system. We demonstrated super resolution imaging in turbulent phantom that can be used as a good model of thick tissue imaging. Finally, we identify following space for improvements. Resolution should go closer to 2-fold improvements. Post-processing image enhancement, need for reduction of exposure time for image acquisition. In the end, I would like to thank you for your patience and to thank my colleagues at Tulane University Translational Biophotonics Laboratory and to our funding sources.